Like to thank the organizers for allowing me to speak at this workshop. It's been great so far, and I'm looking forward to the next few days. Particularly in the placement of my talk. So Volodymyr just finished his talk talking about the how primordial black holes can evaporate and the different signatures we can kind of expect. And one of the interesting features of having primordial black hole evaporation is that they can produce any particles irrespective of their interactions with the standard model, and that's kind of interesting. And that's what these two papers from the summer are on the arXiv and recently got accepted into PRD are about, and that's what I'm going to focus on today. One sec. Okay, yeah. So one important aspect, which is touched on earlier, is that black holes don't live forever. They evaporate, as this sketch of Hawking radiation on the left here shows. And that basically means that there are two distinct primordial black hole categories. They may be stable, and we've heard a lot about them this morning. And that means that these primordial black holes, or these black holes, have a lifetime which is longer than the age of the universe. And that corresponds to roughly having a black hole mass of above 10 to the 15 grams. And then on the other case, obviously, there's the other situation where they're unstable. And because of Big Bang nucleosynthesis and other constraints, there are basically very, very strong constraints on the amount of primordial black holes or the population of primordial black holes that you could have that evaporate because they would disrupt Big Bang nucleosynthesis. And in order to avoid those constraints completely, you want to have a lifetime of your black holes such that they evaporate before BBN starts, and that corresponds to having a primordial black hole mass below around 10 to 9 grams. So the radiation coming from the black holes, basically all fundamental particles, because if we see in this Hawking radiation sketch, you can see that this is coming from bubble diagrams, and it's determined by the equation of motion of the particles and not their interactions with the standard model or any other particle interaction. So the radiation will consist of all fundamental particles irrespective of the interactions. And what we know about dark matter is that it interacts gravitationally. It could interact in other ways, but we haven't detected that. And this is a feasible way of generating dark matter. There are two separate situations here with how you produce these particles, dark matter particles or otherwise. You could have a situation where the initial black hole temperature is already hot enough or hotter than the mass of your particle that you want to produce. And that basically tells you that you're going to produce this particle throughout the entire lifetime of that black hole. So that throughout this whole period, we're producing the dark matter particles or any particle that you're interested in. Alternatively, you could have a particle that you're interested in, or a particle in general, which is heavier than the initial black hole temperature, but because the temperature of black hole is inversely proportional to the mass of the black hole, as it evaporates, its temperature increases, and then will, at some point during the evaporation, enable you to produce such a particle. So in an expanding universe, a dynamic universe, you basically have, if you want to track or look at the number of dark matter particles that are being produced, that exist, and their density and how it evolves over time, you go with the normal Boltzmann equations, and now we have this source term on the right where black holes produce dark matter, and this depends on the black hole mass as well as the spin of the black hole. Like in other production mechanisms, what usually happens is you have some sort of physical process which produces a number density of of dark matter of particles that you're interested in in early times, and you track that using entropy conservation to the temperature of the universe now, and that goes goes like this: fraction to the power of 3. And here in this case of evaporating black holes or primordial black holes, the temperature that you're interested in is the temperature of the universe at evaporation or around evaporation. And this power of 3 basically makes you extremely sensitive to what that temperature is. And the number of primordial black holes can sufficiently affect by evaporation, by basically injecting entropy into the standard model bath. It affects the temperature of the universe in a non-trivial way, and it affects this temperature, so it can really affect the kind of precise value which you expect of the relic density. So what we decided to do is we decided to develop a code which tracks all the relevant equations, Boltzmann equations, coupled and in a coupled system of Boltzmann's equations, and basically can track the evolution of the universe with the different populations of things, including, so here I'm showing just a case where there is no dark matter, and we have on the left here a case where primordial black holes dominate in early times, the energy density, and here we have the situation where they don't dominate and can continue kind of as normal, but there are black holes producing potentially heavy particles. So this code is available publicly through Ulysses, which is originally a leptogenesis code, but now includes dark matter, a dark matter suite. And one of the motivations for doing this was we felt that the full kind of generality of dark matter production just from primordial black holes hadn't been explored with as much precision as we'd like, i.e. tracking the evolution of the universe and all the populations. And also we wanted to make this code publicly available so other people could use it. And here on the left, I show a plot, which we'll see again, which is basically telling you, these lines tell you for a given dark matter mass, they tell you what the fraction of primordial black holes you need. The speed parameter is a fraction of primordial black holes when they were initially produced over the density of the total universe, or the energy density, the total energy density of the universe, against the mass of those primordial black holes. Here, I'm assuming a monochromatic signal. And basically, these lines are the lines where you produce the correct relic abundance according to Planck. Okay, and so the solid lines here are full calculation with the system of coupled Boltzmann equations, and the dashed line is using the approximations that we found in the literature using geometric optics limit and stuff like that. So we see there's a substantial difference here. And also what I just showed previously was assuming the dark matter was a fermion, and here on the left I show how these lines of correct relic abundance differ given different spin states or natures of your dark matter. So so this dash dotted is a spin 2 particle, and dashed is the vector dark matter particle. Dotted is your fermion, and the solid line is your scalar. And the left and the right plot basically show you the difference that you get if you have a population of primordial black holes which are maximally spinning. And we see here, especially, like I think this was alluded to in Volodymyr's talk, that the spinning black holes emit high spin particles much more readily. And this here we can see, if we compare the spin 2 dark matter particles, that the relic abundance kind of line is substantially different. And so we had a second paper which followed up from this, and it built up from this, and basically we wanted to explore the interplay between interacting dark matter models and primordial black holes. And the reason we did this is because we think it's important to understand what kind of scenarios might be inconsistent. For example, phrases like the question that spurred me on was like, could future detection of dark matter constrain primordial black hole fraction in the region of interest. And the way we did this is we basically added interacting dark matter particle with a U1 vector mediator, and by having the system of Boltzmann equations, we're able to track what happens for specific parameter points. But then that allows you to, systematically explore the parameter space region. And for example, here I'm showing a region where we explore for a freeze-in dark matter case, where the existence of primordial black holes substantially affects the cross-section that you'd expect in order to get the correct value. So this is a short talk, so I won't carry on anymore, and I'll just say thank you very much, and I'll let this my teaser video talk run while I take questions.